Hey guys, so we are going into lesson 1.2, so we're going to do more with limits, and I'm going to introduce to you the intermediate value theorem. Okay, so last time when we talked about limits, we were looking at graphs, and then we talked about if there wasn't a graph that we could use direct substitution. Remember, that's always the first step to see if there's direct substitution in there. If direct substitution does not give an answer to a limit problem because the indeterminate form is obtained, meaning 0 over 0, or in some cases, again, this will be later, infinity over infinity. That is what we call indeterminate, okay? We have to use the algebraic techniques to change the form to be able then to take the limit. So of course, first you try direct substitution. If we come out with the indeterminate form of 0 over 0 or infinity over infinity, then we have to see if there's some way that we could have simplified before we do another direct substitution, okay? So as you can see here, if we were to plug this in and we plug in 0, we would get 0 over 0 times 0 plus 1, which is our 0 over 0. Now, I'm going to show you that that is 0 over 0, but on a test, you are not allowed to put that down. It does not want to see this because this cannot happen, okay? So I'm just showing you like, hey, if this happens. So one of the good things that we can do is get rid of this equal sign because I'm no longer saying it's equal there. But as you can see, if I go back up here, what can happen when we simplify? Well, x over x can cancel. So now I have to rewrite this. So you have to rewrite the limit. Get used to it, right? Rewrite the limit or you're going to lose points. So limit as x approaches 0, but now because x over x cancels, I'm left with 1 in the numerator and x plus 1 in the denominator. Now I can do a direct substitution and have 1 over 1, which of course is 1. Now there is a limit because both sides are going to it, but it's not an exact value because what actually happens is there is a hole at 0. Okay, so let's try number 2 here. So if I do again direct substitution, I would get 0 over 0. So let's think about how we can change the form and simplify it. So I'm going to rewrite it, limit as x approaches 2. So the numerator I can't do anything with, but the denominator I see is a difference of squares. So it's plus 2 minus 2, and now we can cross off. Let me rewrite it again. Limit as x approaches 2. What's left in the numerator is 1. What's left in the denominator is x plus 2. Now if we do direct substitution, we get 1/4. What happens because these crossed off is there is a hole at 2. Number 3. Okay, first of all, this, of course, is 0 over 0, so we have to simplify it. So let me rewrite it. Limit as x approaches 1. Now, this, if you remember, is an identity, polynomial identity. It's your cubic identity. So if you can't remember how to do that, you can either use synthetic division, long division, or we can just memorize the identity. So we go x minus 1 because we're minus, okay? And then we have what's left over is an x squared plus x plus 1. Okay, all over x minus 1. Now, for those of you who are doing long division or synthetic to be able to factor this out, one of the things all you care about is this x minus 1, because that's our problem. So why would you try anything else? So remember synthetic, by the way, you would do opposite to what we see. So we would do positive 1. We would have 1x cubed, 0x squared, 0x, negative 1. Remember what we do, we bring down, multiply, add, multiply, add, multiply, and that's where we get our x squared, x, and 1. For those of you who have no idea what I'm talking about, make sure that you put a star next to this number and make sure you ask me questions next class so I can show you how to do this. Now, are we going to run into the cubic identity a lot? No, it will appear once in a while. All right, so we know now that those cross off. Because they cross off, remember there's a hole there. And that gives us limit as x approaches 1 of x squared plus x plus 1. So when I plug 1 into that, I get the value of 3. All right, so again, synthetic, or you could have done long division. Okay. All right, 4. 4 gets a little bit tricky, okay, because we have that square root there. Let's double check. Square root of 1 is 1, 1 minus 1 is 0, 1 minus 1 is 0. So I get the 0 over 0, the indeterminate. So there must be a way to simplify, okay? One thing I noticed right there is that square root, and that square root is always the problem. So let me start with the problem. Let's get rid of it. The one way to get rid of it, guys, is to multiply by the conjugate. So that's keeping the first term the same, changing the sign, and keep the last term the same. But we also know at fractions that whatever we do to the bottom or the top, we have to do to the other. So I'm going to multiply both top and bottom by the square root of x plus 1. Okay, so you're going to have to FOIL this out, rewrite your limit. I will take off points. This will help you in the long run. Okay, limit as x approaches 1. So on top, when I FOIL out, I get x minus 1. And on the bottom, I don't need to FOIL it out. So always remember that the top or the bottom, depending on which one you're changing. Right here, we're changing the top. So we need to FOIL the top and not the bottom. But if we were changing the bottom, we would FOIL the bottom, not the top. Okay. And the reason why we don't need to FOIL the bottom is, as you can see right here, this x minus 1 now cancels with top and bottom. Let me rewrite that so I can see what we have. So it no longer is an indeterminate. So we have 1 on top, square root of x plus 1 on the bottom. Direct substitution, we end up with 1 over 2. And again, there's a hole there. All right, on the bottom here. First of all, we have a limit as x approaches 2, and it's to the right. So on the right side, we have x over x minus 2. All right, so first of all, if we plug in 2, we get 0 over 0, or we get 2 over 0, okay? Which means we have an asymptote right there, right? We can't really simplify that with knowing there's an asymptote at 2. The problem is we got to figure what is happening on the right side of that asymptote. So think of this. So the right side of 2 would be like 3, 4, 5, 6, 7, 8, all the way to infinity, right? So if I plug in 3 on top, I would get a positive 3, and on the bottom, I would get a positive 1. Okay, so what happens there? You can test another value out. Test 10. That would be positive 10 over positive 8. So it's a positive over positive. What is the highest positive value we can get to? The highest positive value we can get to is infinity. So looking at that behavior of that vertical asymptote, that means we can either put this limit as a positive or infinity, or remember we learned last time, or we can say does not exist. we have to get used to seeing it both ways because we don't get to choose a multiple choice. Okay, but really there's a vertical asymptote at 2, so we needed to figure out which way that graph went using algebra. All right, 6, discuss the continuity of this piecewise function. All right, so first of all, what we want to do is we're just going to talk about what's going on, okay? Discontinuity, so we need to talk about holes, asymptotes, jumps, anything like that. And we can analyze everything in here. The easiest one to do first is to see if there is a jump, okay? The way that is, well, actually we can't. First we have to simplify everything. So never mind on that. Simplify everything first. So first of all, let's factor this. This is x minus 3 times x plus 1. Okay, so as you can see right away, if these two cancel, that means there is a hole at 3. Now, to find the y value of that, all we would need to do is plug in that value of 3 to what's not crossed off. Okay, those are crossed off, so that's a hole. When I plug that in, we get 3 plus 1 is 4. So there is a hole at 3, 4. And as you can see, we have a point here at 5, 3, which means all we have in this idea is a hole. So it is a removable discontinuity. Okay, really what this graph is going to look like, guys, is that the top piece is this x plus 1. But what happens is at 3, there is a hole to that line. But there is a coordinate pair at 3, 5. Okay, so it looks like that. All right, look at 7. If this piecewise is a continuous function, find the value of a. So here is, oh, I guess my light didn't work. Here's what I want to point out. You already know it's continuous. So what does that mean? That means on the graph, I shouldn't have to pick up my finger. So in actuality, what that means is when I plug in 2, they come to the same value. Okay, so again, let me repeat that. Because it's continuous, they state it's continuous. What we're doing is that at 2, they have to be on the same point. So they have to equal each other. Okay, so I'm going to plug in 2 for x. So I get 3 times 2 squared plus a. And because we want it continuous, it equals 2 minus 3. And then what do you know? Since we only have one variable, all we have to do is solve. So I get 12 plus a equals -1. So a equals -13. If a were any other value than -13, this would not be a continuous function. All right, let's see if we can use tables to find limits, okay? So I already have this in my calculator, so that way you guys don't have to wait for me to type it in. One of the things I do want to point out, but because my light is off, you can't see it. Let's see if I can do that. Yeah. My numerator is in parentheses, and so is my denominator. The other thing about this table is, as you can see, we are going really, really small, okay? So you can go to your table, which is second table, and what you might want to do, let's see, let's start at 0.09. So go to table set, second window, and I'm going to start at 0.9. And then table again. So at 0.9, if I look at my calculator, I am at 5.6 0.7368. The other thing you guys could do on your calculator, and I wish it would show up, is if you go to graph, okay, it doesn't matter if you see the graph or not, but what you can do is go second calc, go to value, and then plug in that. So I'm going to put in 0.99, and I get 50.749. Okay, I can do that again. Second trace, go to value. Sorry that my hands are shaky. 0.999. Okay, and then get 500.750. Okay, and I'm going to keep going and do this for you. So I get negative 499.250, negative 49.249, and negative 4.238. All right, so first of all, we're saying the limit at 1. So now we're looking very, very close to 1 here, which falls right here. Is your left side and your right side going to the same number? Yes or no? The answer is no. One's positive and one's negative. So that means this limit does not exist because they're going to different numbers. Okay? Now let's check on the other one. Same idea, but we're going to put in those values. Okay, you can put them into your calculator yourself. I'm going to give you these. 0.272, 0.327, 0.333, 0.334, 0.338, 0.384. Okay, now this is limit of 2, so 2's around here. Are they going to the same number? Yes, they are. Now, if we got in closer on our table for our calculator, you will see that it will be 0.333. Okay, you could put 1/3 if you want, but 3 decimal places is just enough. Now let's ask ourselves, can a table like these be used to find limits with absolute accuracy, with absolute certainty by looking at a table? The answer is no, because we have no idea what is happening in between the points, okay? There could be something hidden. So mind yourself, no, because there could be a hidden behavior. Okay, you're not able to see all points. You're able to see really close what happens, but we have no idea if we're missing something, okay? All right, one last thing, and of course this went to my stuff, or I don't know what's going on, guys. Technology, craziness, right? All right. I know it's still recording and I can't figure out on what I did. Let me try this. I'm sorry, guys, I'm wasting time. Okay, yay, I'm getting somewhere. Okay. Sorry, guys. Hold on. Let me pause the recording and figure this out. Okay, I think I figured it out. I messed up too, guys. Okay, one last part. The intermediate value theorem, okay? So let's look at this in parts, okay? So first of all, you can only use the intermediate value theorem if f is continuous between on a certain interval, Okay, so it has to be continuous. So no holes, no asymptotes, no jumps. It's continuous. So this picture here shows that it's continuous from A to B. Okay, and there is a K value, which is a Y value, between F of A and F of B. Okay, so 1 is continuous. 2, the K value has to be between F of A and F of B. If both of these happen, then there is at least one C value between A and B that F of C equals K. Okay, so there are 3 things there that we need to go through. Describe the intermediate value theorem guarantee. So first we're going to check if C is given on an interval. So let's check one at a time. Is F of X continuous for this function between 0 and 5? Yes, it is. There's no issues with that. So yes, is continuous. So there's check 1. Yes. And we're going to say on 0, 5. And yes, to use the theorem, you have to state these steps. On a test, I will take off points. The second part is to check that your K value is in between your other 2 values. So number 2, what you are going to do is find your A and B value, or your F of A and F of B value. So F of 0 would be 0, and F of 5 is 20. So is 12 between 0 and 20? Yes, it is. So what that means is that you're going to guarantee. So yes, there is a C where F of C equals 12. Okay? Yes, I know this is a pain, but we're going to do this. Okay, G. First of all, I want to point out that's interval. The first thing we look at is it continuous between this? Well, 0 and 3. As you can see, guys, there's a value that we have an issue with. What value is that issue? The issue is the 2. Okay. And is 2 in between the interval? Yes, it is. So we will state G of X is not continuous from 0 to 3. So the intermediate value theorem does not apply. Now, by the way, if we said 0 to 1, it would apply because it would be continuous from 0 to 1. It is not continuous on 2. It's actually a hole there. Okay, so keep that in mind. You have to test that out. Okay, number 10, last one. Find the value of C. So right here, I proved that we could work it out, right? So now what we're going to actually do is find that C. So what we do is we set our equation, and we're going to plug in C, and get 12. So I'm going to plug in C to our equation right here. So I get C squared minus C equals 12. And now we're going to solve. It's a quadratic, so I'm going to have to move everything to one side and factor. So I get C minus 4 times C plus 3 equals 0, which means C is 4 and C is negative 3. Now there's one more thing you have to keep in mind. Our interval was from 0 to 5. So I've got to check that that worked. This does not work. So the only value is that C equals 4. All right, there you go.